Okay, so here's my 74HC595 in action. So I've got 6 LEDs linked up to it. And let's just explain what's happening here. So the 74HC595 is here, hidden behind this enormous rainbow coloured 6-way cable. And what I'm doing here is I'm feeding in on the right side 3 inputs from the Arduino. So I've got the Arduino here connecting up, providing power at the back here, and also providing 3 control lines coming in to the chip here, which has then got 6 outputs. There's actually 8, but I'm only using 6. They come through this colourful cable here and to the 6 LEDs. And I've got my single inline resistor package, and the whole thing's finally grounded down here. This is just the ground, and then there's a power for the chip itself. And there's a couple of other wires, because you've got to take the output enable low in order to get anything to happen. And you've got to take the, you mustn't do a clear. So I've connected the clear pin up so it isn't continually resetting the whole thing. Now, if we look at the code, it's quite a simple thing, because I found this Hello World shift out code, which is one of the standard Arduino examples, and it just sets up pins 8, 9 and 10, which are my orange, red and brown wires. They all go into output mode, and I go through 2 loops displaying an 8-bit number on my 6 LEDs. So obviously 2 of the 8 bits are being thrown away. So I display the number 4, 8, 16, 32, 64 and 128, which is how we go from left to right. And then I display 64, 32, 16 and 8, which takes me back over to the left, and then I start all over again. And all you have to do to get your data, your serial data, out to the shift register is, well, there's a debugging line of code there that we don't need. Let's get rid of that. You have to take the latching pin, so the latching action low. You do a shift out, which is a built-in Arduino command. Is it built in, or do you have to include that as a file? No, that is built in, isn't it? And then you just say which data pin, which is your clock pin. MSB first just says we're putting the high bit first, not the low bit first, and then the amount or the value to display. So we're sending, so it actually handles all 8 bits and sends them in one go. And then we latch high to actually do the latching at the end. So that is, so the clock pin is controlling the shift action, and the latch pin is controlling the latching once we've put the data in. Now, what I wanted to do though was an experiment to see if I could chop out the one of the pins and link 2 of the clock pins together. So what I want to do then is take out the latch wire altogether and put a link between the latch wire and the other clock. So I use the clock in one, so I just use one clock for both signals. So let me try that out. Well, firstly, what I've done is I've just taken the pin 9, the latch wire, out. Much to my amazement, everything seems to be reasonably working as it was before, with just a little bit of flicker over on this side. Oh, that's completely out of focus, sorry about that. So that's with the latch pin, that's with pin 8 completely removed. How bizarre is that? I'm not sure why that is, because you shouldn't really leave an input floating like that. So let's now link pin 8 and pin 9 together. So that's interesting. So now I've linked pins 8 and 9 together. So I'm only using one clock, and this the middle pin I'm not even using at all. I probably should just pull that away so it's not confusing things. And it's sort of working. Really is sort of working, apart from it's only lighting up the first 5 lights and not the 6th one. It was actually working better when that wasn't plugged, when they weren't connected together. That is strange. Now, if you try and trick the system a little bit and think to yourself, why not link the serial clock or the serial in action and the R clock together? So I'll link those 2 pins together. I'll do the shift action and the latch action at exactly the same time. What you would think would happen, at least what I thought would happen, would be that 1 bit of data would go into the shift register and then it would instantly become available in the parallel register. Then you'd shift another bit in and it would instantly become available in the parallel register. But that is actually not the case, and the creators of the data sheet have thought of this. So if I just search in this data sheet for together, here we go. Both the shift register clock and storage register clock are positive edge triggered. If both clocks are connected together, the shift register always is 1 clock pulse ahead of the storage register. So the shift register is always 1 clock pulse ahead of the storage register, meaning that if you link both the clock pins together, it seems that this latch action is performed slightly before this shift action. So if you imagine a condition where the shift register has got all zeros in it, let's just do that now, shall we? Can we do that? Yeah, we can. So the shift register's got 8 zeros in it. The parallel register's got 8 zeros in it. And we normally we would shift in, let's say we shift in a 1, we'd expect the 1 to appear just here. And then we'd latch and we'd expect the 1 to move up to here. But it doesn't work that way because, as it said in the datasheet, if you link the clocks together, the latch is 1 clock step behind the shift action. So if you link the 2 together, when you do an action, a clock pulse, first it latches 0 into 0, then it would shift in at 1. So nothing would appear at your output buffer. Then we'll put in another 1, so it will latch our 1 and loads of zeros into here. Then another 1 will get shifted into our shift register. So again, we've put in 2 1s, but we'd only see 1 on the output buffer. And that's why when I was trying it out, I was getting a bit confused because I was trying to send in 6 different lights. I was only ever getting 1 of the lights show up. I was only getting 5 of the lights show up. And the reason is because the output buffer is 1 clock pulse behind the input. So what I think I need to do is send 1 extra clock pulse at the end after I've shifted my data in, just to flush this pattern here into here. Well, of course my pattern would look something more like that because I only want to have 1 light on at a time. So then this 1 would come out here and one of my LEDs would light up. Okay, so I've come up with a theory that what I'm missing is 1 extra clock pulse. So what I'm doing now is, well, I'm sending the latch pin low, but I don't need to because the latch pin isn't even used anymore. So let's get rid of that. I'm shifting the bits out, taking the latch pin high, well that's not needed either. And then I'm doing a little sneaky pulse on the clock pin from low to high. Possibly I should take it from low to high and back to low again. Let's try that. Oops. Let's do that. Low to high and back to low again. Then I'm going the other way. So again, I've got stupid lines of code I don't need. And then we'll go from low to high and back to low again to put my 1 extra pulse in. Well, let's try this out and see if it works. Well, it does. Look at that. That is quite amazing. So yeah, I think I've cheated the system there and managed to get exactly what I wanted. 6 LEDs lighting up nicely with a little bit of background flicker using only 2 Arduino pins. I'm pleased with that. That's actually almost good enough to use, isn't it? Now, in conclusion then, so firstly I've used Charlieplexing, and Charlieplexing is very simple, but it's only good for up to 6 LEDs, because once you go above 6 you need 4 pins, so it starts getting a little bit expensive in the pin count, but it's very cheap in the component count, because you only need 6 LEDs, 3 resistors. However, you can only have one of the LEDs on at a time. Now, if you use the shift register, it's much more expandable. Obviously, you've got to find yourself an extra, well, you've got to find a place to put an extra chip on your circuit board. You're going to use a little bit more power, because you've got to power the chip, a tiny bit more current. You've got to use more resistors, because you need one for each LED, but it's much more extensible, because I could easily do 8 LEDs here, either 3 Arduino pins with no flicker, or 2 Arduino pins with a little bit of flicker. And then it's much more extensible, because you could stick another chip right next to it, chain the two together, and we could have 16 LEDs off of 3 pins, or 16 slightly flickery LEDs off of 1 pin. And also you can light more than one LED at a time, because you can shift out any data you want. You could shift out all ones and light the whole lot if you wanted. But there is a way of having as many LEDs as you want with only 1 pin, which is very, very clever. And the answer is Neopixels. So let's just take a look at some Neopixels here. Well, that's a flattering picture, isn't it? So Neopixels basically are LEDs with 4 wires connected to them. So one of the wires is power, the other one is ground. There we go. That's a better picture. And you can chain them together. So all you've got to do is on each pixel link up the power and the ground. Then you have a serial in and a serial out for each LED. They're quite chunky things. I think these are 8mm through-hole LEDs. And there's an example circuit. So what's going on there is some sort of microcontroller that is talking to those LEDs using only 1 wire, only 1 pin out of the microcontroller, and then each Neopixel talks to the next one in turn. And the very clever thing is they're RGB, so you can have as many colours as you want, and you can get about 16 million colours out of these things as well, rather than my boring old 6 red LEDs next to each other. But you pay a price for it. Look, there's a 5-pack for £7.50 there, so they're quite expensive, and I would imagine draw quite a lot higher current than normal LEDs. So you've got a variety of choices. Take your pick.